Good afternoon, everyone. Today we are going to discuss about the Nyquist stability criterion, and it is also called as a Nyquist plot. In the last class, we have discussed about the Bode plot, how to draw the Bode plot, and how to find the stability from the Bode plot by finding the gain crossover frequency, phase crossover frequency. From that, we are going to get the gain margin and phase margin. So these values will give you the stability of a system. Okay, now today we'll discuss about this is also a frequency plot, which is called as a Nyquist plot. It is also called a polar plot. Okay, so the Nyquist plot were invented by a Nyquist who worked at Bell Laboratories, the US. Now, the Nyquist plots are a way of showing the frequency response of a linear system. Okay, so there are several ways of displaying the frequency response with the help of a Bode plot and Nyquist plot. So the Bode plots use the frequency as a horizontal axis and use the two separate plots to display amplitude and phase of the frequency response. Okay, so this is called as a magnitude plot and a phase plot we have seen. Now, so the Bode plot, which we have taken it as a consisting of a magnitude plot and phase plot with the variation of frequency. Okay, but the Nyquist plot is one which is taken only a single graph, which is nothing but the amplitude versus phase angle. Amplitude versus phase angle. So can you see the PPT? Can you see the PPT now? So here, the Nyquist plots are of showing the frequency responses of a linear system. There are several ways of displaying the frequency response, including the Bode plot and also the Nyquist plot. And the Bode plots use the frequency as the horizontal frequency as the horizontal axis and use the two separate plots. So in two separate plot means we are taking a magnitude plot and phase plot. Now the Nyquist plot displays both the amplitude and also the phase angle on a single plot using the frequency response as a parameter in the plot. Okay, so now the Nyquist plots have the properties that allow you to see whether the system is stable or unstable. Now, a Nyquist plot is a polar plot of a frequency response of a linear system. And this means that Nyquist plot is a plot of the transfer function g of s when we take s is equal to j omega, and that means that this plot will be of g of j omega. So as a g of j omega is a complex number for any angular frequency, so the plot is a plot of complex numbers. That means the complex number is one which is having a magnitude and phase or real part and imaginary part. So the complex number g of j omega depends upon the frequency. So the frequency will be a parameter. That means if you plot the imaginary part of j omega axis, again it's the real part. So you can have a plot of versus, you can have a plot of the magnitude of your g of j omega, magnitude of g of j omega versus phase of j omega, phase of g of j omega, any function now. So this can be now, it is a complex term, so this will be now having a r at an angle of phi. Normally this is a magnitude plot and this is a phase now. Okay, now this can be converted into the complex term which is known as a real part and imaginary part, x plus j y. So you can use any representation for the g of j omega to draw the plot. Normally we draw the plot, okay, versus here the plot of any uh, magnitude versus, okay, this is the magnitude versus phase or real axis versus imaginary axis. This is the real axis, this is your imaginary axis. Now we call it as a sigma plus j omega. Okay, this is a complex term. So this is called as a plot, which is a Nyquist or polar plot. Now, the polar plot of a sinusoidal transfer function g of j omega is the uh, plot of the magnitude of g of j omega versus the phase angle of g of j omega on polar coordinates as omega is varied from 0 to infinity. This is very important. So omega, when we have to vary the omega from 0 to infinity, we will get the different magnitudes for g of j omega, and also I'll get the phase angles. So if you draw this phase angles versus magnitudes, you'll get the polar plot. So this is normally we are representing the polar plot into uh, with the magnitude and phase into a real part and imaginary part. So the polar plot is the locus of vectors of g of j omega and magnitude of g of j omega. So versus angle of j omega. So here this is a plot which is drawn after converting the polar coordinates into the rectangular coordinates, because this is a real part, okay, and this is an imaginary axis. So this is the plot of uh, this is the plot, polar plot. This is called as a polar plot, which is varying from, normally this will be now here omega, the plot will be now varies like this, omega will be 0. Okay, so this is a starting point you can take with omega is equal to 0, and your goes on increasing the omega and increases up to omega is equal to infinity. Omega is equal to infinity, now this is the ending point. So we have to see that where the polar plot is starting and where the polar plot is ending. Okay, so the polar plot ends at the origin here with omega is equal to infinity, and when omega is equal to 0, the polar plot starts here. So goes on increasing the frequency, your polar plot. This thick line is the polar plot. So we'll see how to draw this plot with the different frequencies. Okay, so here this is the angle of g of j omega. Okay, and this is the imaginary part, and this part is a real part. Now, so each point on the polar plot represents a terminal point of vector with variation of omega. So each point, that means here this dot, each point on the polar plot with the variation of omega. Now projections of geometry on the real axis and the imaginary axis are its real and imaginary components. Now the polar plots are drawn for the minimum phase and not only the minimum phase systems. Okay, so what are the minimum phase systems and non-minimum phase systems? So the transfer functions are having neither either having the poles and zeros on the uh, right half of the S-plane, they are called as the minimum phase systems, and whereas those systems which are having the poles and zeros on the right half of the S-plane. Okay, so if is any pole which is located on the right of the S-plane, then those systems are called as a non-minimum phase systems. If any pole or zero, okay, which is located, not located on the neither. So this is a neither poles nor zeros, which are on the right half of the S-plane. Those systems are called as a minimum phase systems. If any poles or zeros which are located on the right half of the S-plane, which is called as a non-minimum phase systems. Normally, we'll draw the polar plot for the minimum phase transfer functions or minimum phase systems. Now, this is a Nyquist plot. So, the advantage of the polar plot is that for over a wide range of frequencies, we can get the frequency response characteristics on a single plot. This is the main advantage of a polar plot. But the disadvantage is that we cannot know the individual contributions of the factors. So factors means we have seen the k by s and first order factor, and the denominator or first order factor in the numerator, and the second order factor in the numerator and denominators. So a transfer function will consisting of all these factors. So you cannot find out what are the individual contributions of these factors in the polar plot. Okay, so now, so how to sketch the polar plot now? So to sketch the polar plot of a g of j omega for the entire range of frequencies, that is the omega is varied from 0 to infinity. 0 to infinity, there are four key points which we usually come across. So here we need to take up the starting point of a plot with omega is equal to 0 and the ending point, okay, the where the polar plot ends when omega is equal to infinity, and where the plot crosses the real axis and where the plot crosses the imaginary axis. We have to find out all these points. Okay, so in previous case we have seen that the plot will be like this. Okay, so here it is starting like this. Okay, so the polar plot is starting here. That means here when omega is equal to 0, so this is a starting point of the polar plot. Okay, so in this way it is moving. As you goes on increasing the frequency, the polar plot points will be moving in this direction. Okay, so now this plot is ending at this point where your omega is equal to infinity. Omega is equal to infinite. In this process, this is crossing the real part. Okay, so where it is crossing this, so this is the third point. Okay, where the plot crosses the real axis, it may be in the negative real axis or positive real axis. So for that case the imaginary part will be 0. The imaginary part of j omega will be 0, and then you can find out where this is crossing on the real part, negative real part. Okay, now if you take up that another transfer function, this will be in polar plot, this will be like this. Okay, so this is your plot may be starting here. So this plot is starting here with omega is equal to 0. Okay, and this is crossing your imaginary axis as omega is increasing. So as omega is increasing, this plot crossing here on the imaginary axis. So here the real part of g of j omega will be equal to 0. So you can get that point, you can get this point, and also you can get the value of omega. And here also if you see that here the polar plot is crossing the real part. Okay, so here the imaginary part of g of j omega will be 0. G of j omega will be equal to 0 here. And now this will be the ending point where your omega is equal to infinity. Okay. So here the first one, the starting point with omega is equal to 0, okay, and the ending point with omega is equal to infinity. In between the polar plot crossing the real and imaginary parts. You can also see one more graph like this. Okay, so this may be starting here, and this may be ending here also. Okay, or this may be starting here, and it may end here, and another plot. This may start here and it may end here. It may not cross the imaginary part. Okay, so and so there may be different possibilities. You can see that. Okay, so your plot will be like this, or your plot may be like this here, like this. So these are the different possibilities, different polar plots with the starting point. So always you can see that the starting point. So I'm here drawing the starting point with the, it may be for some constant value or it may be from infinite. So like this. So this is maybe starting from infinite, and this may be starting from infinite here, and here this is starting with some constant real part. Real part is there here. So like that, the polar plot will be starting and ending in the given as plane. So we have to see that how to find the starting and ending point without calculating its magnitude and phase angle directly. Okay, we'll see that. Then we'll go through the problems. We'll see again how this polar plot starts and ends for a given transfer function. Now, I'll see that the starting of a polar plot of all pole minimum phase systems. Okay, so I will take a S-plane here. I will draw the S-plane here. So this is my S-plane. Okay, just remember this. This is your S-plane. So where the start? So starting means your omega must be equal to 0. With omega is equal to 0, your polar plot starts. So always the polar plot starts here. Okay, for this is the start of, this is the starting point, start of polar plot, start of polar plot, start of polar plot for type 0 system. So we see what is a type. Okay, so this is a type 0 system. Okay, and this is a starting point. It may be starts at infinity or with some constant value when your omega is equal to 0. So when the system is of type 0 system, this is the starting point. Okay, so this is the starting point for type 2 systems. This is the starting point for type 2, not type 1 system. And this is the starting point for the type 2 system. Okay, this is the starting point of type 2 system, and this is the starting point of type 3 system. This is the starting point of type 3 system. Always the polar plot starts from these points. It may either may be 0 or constant value or from the infinity. So these are the starting points of any type of a system. So you know that what is the type of a system? Normally the type of a system is obtained for the open loop transfer function g of s into h of s. G of s into h of s will be equal to, normally we know that this is a s plus some b1, okay, into s plus b2, s plus b2, and also on s plus bm, s plus bm divided by s power n, s power n. Okay, so you can also call this as a z1. So because this is called as a 0, so s plus z1, s plus z2, s plus, and so zm divided by s into s plus p1 and s plus p2, okay, and so on up to s plus Pn. So these are the poles. So here for if the power of s, okay, so here the power of s power n, this power s power n will give you the type of a system. Okay, if n is equal to 0, if n is equal to 0, this is called as a type 0 system. Am I right? So this is a type 0. If n is equal to 1, and this is called as a type 1, 2, it is called as a type 2, and so on. If it is n, this is a type n system. So that means it is a open loop pole. So this is the open loop pole which is located at the origin, that will give you the type of a system. Okay. So by using this, now you can find out that your polar plot is always start for a type 0 system. That means s power 0. So no s single s should be present in the origin. So that is nothing but your s power 0. So which is a starting point of a polar plot. Now, where the polar plot ends, always the polar plot ends at the origin. So the polar plot ends at the origin here. So now the plot will be now ending here. I'll take a one. The polar plot ends here. So always the polar plot is ending at the origin. Okay, so the polar plot ends like this. This is the ending point of a polar plot. Okay, so this ending point of a polar plot will be depends on the order of a system. It depends on the order of the system. Okay, so this is the end of, this is the end of polar plot. This is the end of polar plot for type, not type, sorry, this is the order 1 or first order, end of a polar plot for first order. So this is the first order, and this is for end of a polar plot for the second order system. Second order system. Okay, and now this is the end of a polar plot for third order. Third order system. Third order system, and this is a for the fourth order. Fourth order system. Am I clear here? So the start will be here. Okay, for type 0, start will be here for type 1. This is for type 2, type 3. Okay, start will be at the infinite values. Now the end will be at the origins, and therefore the polar plot will be ending at these points, and here in the fourth quadrant for the order 1 system, and third one for the second order, and third order and fourth order. So let us assume that our system is g of s is equal to, let us an example, g of s is equal to some constant k into s plus 5 divided by s into s plus 1 into s plus 3. So this is a given system. So for this system, we need to draw the polar plot. Okay, rough plot should be drawn here. So to draw the rough plot now, I'll taking this point here. This will be like this. Okay. So what is the order of a system now here? The order will be now denominator value. So this is the third order system. Order will be equal to, order is equal to 3, and type will be s power 1. So the type of a system is type 1 system. So your polar plot should start from type 1. So that means here type 1. Okay, so we need to take up that omega must be equal to 0. So polar plot will be drawn with omega is equal to 0. So this is a starting point. When you take up omega is equal to 0, so because it is a j omega. So your transfer function can be drawn as g of j omega will be equal to k into 5 plus j omega, 5 plus j omega divided by j omega, okay, into again 1 plus j omega into 1, or this is a 3 plus j omega. I'm replacing the sign s with the sinusoidal transfer function. Now you substitute omega is equal to 0. Your omega will be now 0. So 1 by 0. So whatever may this value here, 1 by 0 is nothing but infinity. This is the infinity now. So we know that type 1 system will be here. So this is the starting point now. So this is the start of the infinity. The magnitude will be now infinity with omega is equal to 0. Omega is equal to 0, your magnitude will be infinity. And now with omega is equal to infinity, 1 by 0. So it will be 0. The magnitude will be, ending point will be 0 and starting point will be infinite. At the infinite magnitude, and here omega is equal to infinity, the magnitude will be 0. Okay. So with omega is equal to 0, the magnitude will be infinity, and with omega is equal to infinity and the magnitude will be equal to 0. So that means your starting point will be here omega and ending point will be 0. So omega is equal to infinity here. Now how it moves, we know that here this will be moving here or not. So we have to see that. Okay, so our system is type 1 system, so you know that this is a starting point. Okay, it may be starting here or it may be starting here, but this is a type 1, so it will be starting here, and order 3, because order 3, so your transfer function or your polar plot end at this point. So here your plot will be drawn like this. Okay, so this will be drawn in this fashion. Okay, so this is a polar plot of a given transfer function. This is a polar plot of a given transfer function. Okay, so directly you can know. Then if you see the angle also here with omega is equal to 0. So tan inverse of 0, 0, 0. So it is minus 90. Tan inverse of minus 90. So always it is starting from this point. Okay. So if the system is type 0, let us assume that type 0 system and order 2. Order 2. Okay. So let us assume that type 0 and order 2. So type 0 means it should be now s plus 1. So there should not be any value s plus 1 into s plus 2. So this is a second order system, and s power 0. So type 0 means s power 0, so is equal to 1. So this will be drawn like this. Okay, so type 0, so it will be starting here, and type order 2, so your polar plot will be drawn like this. Okay, so this is a way of directly writing without going for the mathematical analysis of a polar plot. Okay, so now we'll see the problems. Okay, so just consider the first system. Now I'll consider the system with g of s is equal to 1 by s. So it is a type 0 and order 1 system. Alright. So for the systems, how to find out that? So first of all, any polar, when you want to plot the polar plot, you need to take up g of j omega is equal to, now replace s with j omega. Okay, so now replace s with j omega, 1 by j omega, which is equal to now minus of j by omega. Now what is the magnitude of this plot? So 1 by omega. The magnitude will be 1 by omega. Just you remember this. This is the magnitude. For every system, you have to find out the magnitude and the phase angle. Phase angle will be now minus 90. So this is the magnitude and phase. So you need to find out the magnitude and phase angle for a given system. Now you have to substitute with omega is equal to 0. With omega is equal to 0, your magnitude will be 1 by 0. So your magnitude will be equal to infinity. Am I right? So with the omega is equal to 0, this is omega is equal to 0, your magnitude will be infinity. Okay, and then with Omega is equal to 0. What is the magnitude again? This is a minus 90. So it is not varying with respect to omega. So always it is located in the minus 90 degrees. Okay, so this is a, normally we'll take this is a plus 90 degrees. So the values will be taken as a plus 90 and this is a plus 180 degrees. Okay, and now this will be now plus 270 degrees. Okay, now if you move in this direction, in the clockwise direction, this is going to be minus 90 degrees. Okay, and this is going to be minus 180 degrees, and here this is going to be minus 270 degrees. Okay, so this is a way of taking the angles for any system. Now your plot is having a minus 90 degrees, so always this will be minus 90. So minus 90 should be taken along the negative imaginary axis always, and here this magnitude is varies with the omega is equal to 0 to omega is equal to infinity. This will be 0 and here this will be infinity. So the magnitude is varying from infinity to 0, so this will be infinity to 0. So this omega is equal to infinity here and omega is equal to 0 here. And we have seen that the Bode plot here. The Bode plot can be obtained as 20 log of g of j omega. So 20 log of the magnitude of g of j omega. This is a 1 by omega. So this 1 by omega can be taken as a minus of omega. Okay, omega inverse when you take up in the numerator side, and this will be taken as a minus. Okay, so your plot will be drawing like this. So this is a Bode plot for a given uh, first order term 1 by s. Okay, so this is a polar plot. This is a polar plot for the first order term 1 by s. Now let us consider the second one, 1 by 1 plus st. Okay, 1 by 1 plus st. So this is a term which we are considering. Now what is a g of j omega now? G of j omega is equal to 1 by 1 plus j omega t, because you are replacing s with j omega. Now what is the magnitude here? 1 by under root of, so normally this can be represented as here. This is a 1 by under root of 1 plus omega into t whole square at an angle of tan inverse of omega t. So this is a complex form into polar form, and in this the magnitude will be here. This is the magnitude. This is the magnitude of this one. So 1 by root of 1 plus omega square into t square, and the phase angle will be now minus. If you take up the numerator side, this will be minus arc tan. Arc means here minus tan inverse of omega t. Now, so here if you start this, omega is equal to 0, 1 by 1 plus 0, because your transfer function is 1 by omega square into t square. So the magnitude will be root of 1 plus omega square into t square, 1 by omega square into t square, and therefore when omega is equal to 0, your value will be 1 by 0, so this will be equal to 1, and the phase angle phi is equal to minus, normally this is a tan inverse of omega t, so the phase angle is minus tan inverse of omega t, and therefore this will be minus tan inverse of 0 1, so this will be 0 degrees. Okay, and now with end of the plot, now ending plot means when omega is equal to infinity, so 1 by infinity, so the magnitude will be 0 and your phase angle will be minus 90 degrees. Phase angle is minus 90, here the phase angle is plus 90. Now when omega is equal to 1 by the same crossing point, so it will be equal to 1 by root 2 and the phase angle will be equal to minus 45 degrees. So that means here the polar plot is having the magnitudes of omega is equal to 0. When omega is equal to 0, the magnitude is 1 and the phase angle is 0. When omega is equal to 1 by t, the magnitude will be 1 by root 2 and the phase angle is minus 45. When omega tends to infinity, your value will be here 0, the magnitude will be 0 and the phase angle is minus 90. So your angle is only varies between 0 and minus 90. So this is the first order term, which is called as a corner frequency. Up to the corner frequency, it is having a 0 decibels, and then we are having a variation like this. Okay, so we'll lose some 3 decibels for decade here. Okay, and your first order factor will be varying from 0 to minus 90, and this is a minus 45 degrees. What we have seen for first order terms in the denominator or the border plot. Okay, so this is a representation of border plot, and this is the polar plot now. This is a polar plot with omega is equal to 0. Omega is equal to 0. We need to have a 0 angle. The angle is 0. So you have to start with a 0 angle. Okay, so this is normally 0 degrees. Right? And this is a minus 90 degrees. So this is minus 90. So your phase angle will be 0 and the magnitude is equal to 1. So this is 1. This is having a value of 1. Now, uh, with omega is equal to 1 by t. So when the omega is 1 by t, this is half the value. So same value 1 by root 2. This is a magnitude. When you convert this into real and imaginary parts, you'll get this as a 0.5 and 0.5. Now when you take up omega is equal to infinity, this magnitude will be 0. So it is varying only in between 0 and minus 5. So we see that this is a 1 by 1 plus st, 1 by 1 plus s into t, 1 by 1 plus s into t. So this is a type 0 system, which is called as a type. What is the type of the system here? This is a type 0 system, and this is the order 1, type 0 and order 1 system. And therefore, as per our uh, theory now, this is a starting point of type 0 system. Am I right? So this is a, where here, this is a starting point. Now your polar plot is starting here. Polar plot is starting at okay, so here at this point, this is the starting point with omega is equal to 0. Okay, now order 1. So order means this is the ending point. This is the ending point, and this is a starting point. So you can have a graph like this. Okay, because the magnitude is 1, so this is 1, and here omega is equal to infinity. So same we are getting here for the analysis. So this is a start of the polar plot, and this is the end of a polar plot. Okay, this is starting point, this is a ending point of a polar plot. Now let us take this system. As you know that here, what is the type of the system now? So for this, again s power 0. There is no s term, so s power 0. So s power 0 means it is a type 0 system. This is a type 0, type 0, and order 2. Order 2, type 0 and order 2. And therefore, now you can draw that plot normally here. This will be like this. Type 2, this is a starting point. Okay. So what is the starting point here? So type 0 means it is starts at this point. Okay. And now ends at order 2. So this is the end of order 1, and this is end of order 2. So this should be ending here. So your plot must be like this. The plot must be like this. Okay. So this is omega is equal to 0 here, and this is omega is equal to infinity, like this. So this is the analysis of the system. Okay, now we'll take the magnitude here for this. So what is the magnitude? The magnitude will be now root of 1 plus omega into t1 square under root of omega into t2 square, omega 2 square into t2 square. and the angle will be tan inverse of omega t1 minus tan inverse of omega t2. So when omega is equal to 0, when omega is equal to 0, 1 by root of 1 plus 0, 1 plus 0. So the magnitude will be equal to 1 and the angle will be 0. The angle is 0. That means your plot will be starting here. So at 0 is the 0 angle and the magnitude is equal to 1. Okay, and now the ending point will be now where it is ending when omega is equal to infinity. 1 by infinity, 1 by infinity. The magnitude will be 0, but your angle will be tan inverse of infinity minus tan inverse of infinity, which is minus 90 and minus 90. So this will be minus 180. So minus 180 means this is a minus 90 line, this is a minus 90 degrees line, and this is a minus 180 degrees line, and therefore it will be starting with here and ends with the phase angle of minus 180 degrees. So in this way you have to draw the polar plot. Okay, so if you want to get the imaginary, this crossing points on imaginary point, so you have to convert the given transfer function into real part and imaginary part. Separate this equation into imaginary part and real part, and then equate it to 0. You will get the point where this polar plot is crossing on the imaginary axis. Now this is an important analysis. After drawing the phase plot and after drawing the polar plot, our main aim is to get the gain margin and phase margin. So if you get the gain margin and phase margin, you can conclude that the system is stable or unstable. Okay, so normally here, let us assume that this is our polar plot. Okay, so this is our polar plot which we are drawing here. Okay, so this is my polar plot. Okay, and this is the polar plot with omega is varied from 0 to infinity. 0 to infinity, we are getting this polar plot. Now, this is a unit circle. So this means this crossing on the imaginary axis, we call it as a 1. Okay, always this will be 1. Okay, and this is also 1. And this magnitude is 1. Always this will be 1. Okay, so that's why this is called as a unit circle. Whenever you are drawing the polar plot on the real and imaginary axis, so this should be taken with the equal scale along the all directions of the graph. Okay, so now once you get this, now whenever you draw a line here, okay, so this plot, whenever you see a plot here, a point where I'll take a point here B, so this point, okay, so this is a point where your polar plot is crossing the imaginary axis. You want to see that where your polar plot is crossing the imaginary axis and you measure that length. So you measure this length GB. Let us assume that this is a length which is known as GB, and the gain margin of the system will be equal to 1 by GB. That will directly give you 1 by GB value. That is a positive phase margin. Okay, now let us assume that here you have to take a point. I'm taking with another color here, green color. I'm taking with another color here. This is a line, this is a point where your polar plot is crossing the unit circle. This is a very important concept. You have to remember this. Okay, just see the 2 points. So this green point is nothing but where the polar plot is crossing your unit circle. Okay, so here the polar plot is crossing the unit circle. This is called as a normally phase cross phase gain crossover frequency unit circle. Okay, so this is called as a, because the phase crossover frequency is the frequency at which the gain of a system is equal to 1. The gain of the system is equal to 1. So this point is called as a gain crossover frequency omega gc. Okay, and now the point where The point where your polar plot is crossing the minus 180 degrees line. So this point, the minus 180 degrees line, which is called as a phase crossover frequency omega pc. Okay, so the crossing point on the minus 180 degrees line, this here minus negative real axis, is called as the frequency at this point, because your frequency is varying here. So your omega is varying from 0. So omega is varying from 0 to infinity. Omega is varying from 0 to infinity. It is goes on increasing. Okay, so now here at this point it is crossing minus 180 degrees, and that corresponding frequency we call it as a phase crossover frequency. And now here, whenever it is crossing on the unit circle, we can call it as a gain crossover frequency, because the gain crossover frequency is defined as the frequency at which the gain of a system is equal to 1. So here this is a unit circle, so the magnitude is equal to 1, and here the phase angle is equal to minus 180 degrees, and that's why these two are called as a gain crossover frequency and phase crossover frequencies. So when the polar plot is drawn below the unit circle, then the system is said to be stable, because your phase margin and gaze margins are positive. Let us see why the phase margin is positive here. Okay, now you have to see that whenever whenever your plot here, the polar plot is crossing a point on a unit circle, then you have to draw up a line here. You have to draw a line, okay, like this, and you have to measure the angle here like this. You have to measure this angle. So this angle is called as a phi gc. This angle is called as phi gc. Okay, so from the zero axis, so from 0 to this point, this angle is phi gc, and phi gc will be, now phase margin will be equal to 180 degrees plus phi gc. But you observe that the angle from this point to this point here, so it is minus 180. So this value is always, phi gc is always less than minus 180 degrees, and that's why the net value will be always positive. The net value will be always positive. That means phase margin is always positive. And here also this value, the negative value will be, now it is very smaller, and you have to take the exact value, and this will be again positive. So as per the definition of a stability of a system, the gain margin and phase margins are positive, then the system will be stable. The system is stable. Okay, and now here this is a system. Now you take up this, the polar plot is like this. It is not enclosed by the unit circle. Now it is out of that. Okay, so here the polar plot, now here this polar plot is crossing your unit circle at this point. Okay, so here whenever this is crossing at this point, now your angle will be, phi gc will be greater than minus 180 degrees. This angle will be greater than minus 180, and therefore this 180 degrees minus greater than 180, it is always, because it is a minus 180 plus something, so your angle will be negative. This angle is negative. And here if you see that the gain margin also, it is very higher, and it may be negative. So, and here this point is called as omega gc, your omega gc, and this point is nothing but your omega pc. This is omega pc, where omega pc is less than omega gc. Okay, so then the system is unstable. You can directly see that when omega pc is less than omega gc, the system is unstable. Here omega pc is greater than omega gc. For the first case, omega pc is greater than omega gc. This is a gain crossover frequency. Then the system is said to be stable. So that means that when the polar plot is inside of the unit circle, then the system is said to be stable. If it is outside of the system unit circle, then systems may be unstable. Directly you can get it that. So this is an analysis of determination of gain margin and phase margin, and also the stability of the system. Now let us take that the gain adjustment. Okay, so the gain adjustment is nothing but here I need to find the value of k for a specified gain margin. So normally the systems are defined by k into some 1 plus 5s. Okay, 5s divided by some s into 1 plus 2s plus 1 plus 3s, like this. So this is a system defined. Now I need to find the gain margin, specified gain margin. So what must be the value of k? Okay, so initially here we should don't know the value of k, so we need to find out the gain for specified gain margins and specified phase margins. Okay, so in this case now we have to draw first the polar plot with assuming that k is equal to 1. We have to assume that k is equal to 1, and then you have to proceed further. Then you find the polar plot is like this. Okay, so this is a polar plot which we found by taking k is equal to 1. Okay, then after that now I need to get a gain margin. So the gain margin is defined. Okay, so draw a j omega line with k is equal to 1 now. First of all, k is equal to 1, we have to draw that. Let it cut the minus 180 degrees at the point B. Okay, so the corresponding to gain of GB. Now this is the gain margin which is you are getting with k is equal to 1. So when you assume that k is equal to 1, this is your gain margin which is obtained now. Then after that we need to find out for a specified gain margin. Now let the specified gain margin will be x. Okay, so let specified gain margin will be x. Okay, so if this is x now I need to add up. So what is the formula for the gain margin now? This is a 20 log of 1 by GA. So we need to find out what is the value of GA here because the x is given. This is a gain margin now. So as per this, x is equal to now log of 1 by GA. This will be equal to x by 20, or now 1 by GA. So 1 by GA is nothing but the gain margin. This must be equal to 10 power x divided by 20, or your GA will be equal to 1 by 10 power x into 20. This is the formula now. X here he has given the form direct value. We need to adjust that. Directly you will get a value of GA, and then the new value of k will be obtained by substituting for GA divided by GB. Okay, so if k is greater than 1, it may be moving outwards. If k is less than 1, the polar plot moves right side. So like this, you have to adjust the value of your gain. Now similarly, the phase margin now. Okay, so initially the phase margin is given with k is equal to 1. Now again you have to find out that, and this is the point B here. Okay, this is the point where your polar plot is crossing the imaginary unit circle is nothing but your point. Okay, for a k is equal to 1. Okay, now after that we assume that the given phase margin of x degrees. Okay, and for this x degrees we need to find out 5gc, because if you assume that is given 60, so this will be now 180 minus 60 now, or x minus 180. So your value of 5gc x will be obtained. Once you get 5gcx, now you have to drop a line. So this is a 5gcx now. Okay, so this is another line for the given phase margin. Okay, or this may be, or this may be. So this green lines indicates the required phase margins, and this line will be now with k is equal to 1, the problem is found. Okay, so this green lines will give you the required phase margin for the system. Okay, once you get 5gcx, then you can find out this angle, and you can drop the line, find out the GA, which will be equal to k is equal to 1 by GA. Okay, how to find GA? Once you get this point here, from distance between these two, distance between here will give you GA. So here, this point. Okay, from this point to this point, this is your GA. So it can be obtained like this. So this is a way of adjusting your phase margin and gain margin. And next, let us take a problem here. So we'll solve this problem tomorrow. So do you have any problems now, any doubts? You can ask me now. Do you have any doubts? Okay, thank you all. Tomorrow we'll discuss about the Nyquist plot and then compensators we'll see. Okay. So if you have any problem, any doubts, you can call me. Okay. Okay. You can call me also. I'll clarify all your doubts.